Right.
This is 14.7/11 through 13. So I kind of like picked up chapter 7 and then kind of went to the end. And I'm like, I'm gonna put all this stuff together. So sorry.
Chapter 7.
Chapter, section, unit, whatever you want to call it. Doesn't matter. Today we're going to look at different types of interference, calculate beats, which is super easy, and we will look at the ear, and I can tell you all the gross things that's wrong with my ears. So, here we go. Interference. Constructive interference happens when the wavelengths line up. They end up amplifying the sound because they are all in resonance or constructively interfering or in phase, however you want to call it. So we can make constructive interference by making the sound waves travel different paths. So you have one with a long path and one with a shorter path. And as long as those paths vary by a wavelength or like a number of wavelengths, it's got to be a whole wavelength, then it will be constructive interference. So let's say we have one path and it's 4 wavelengths long. And we have another path that's 6 wavelengths long. Because it's a wavelength unit difference, there's a 2 wavelength difference unit, it will be constructive interference. If you had one with a 4-path wavelength and one with a 4.5-path wavelength, that would not be constructive interference because it's not an integer value. For those of you that need the visual, because I use big words like integer, here's a picture. 4 wavelength. And let's say that this is a 6 wavelength path. And this wavelength, it could be 1 meter. It doesn't really matter what the wavelength happens to be. But as long as it's, some number times the wavelength. When they, let's say they're emitted here, so this is our source. And this is where this is our listener or our observer. Sure. I think it's still vibrating. There we go. All right, so this is constructive interference. Whereas if we did something like this, where this is a 4 wavelength pass, here's your source, and this is a 4.5 wavelength pass, this person, destructive interference. Not going to sound pretty.
So, like, is that like notes?
Yes.
Technically?
Sort of.
Are we going to learn facts about the ears?
I'm going to show you a gross picture of the inside of an ear.
Nice.
Who's the ear?
It's a diagram of an ear. It's not a real ear.
So why would it be gross if it's not real yet?
I don't know. Don't you think anatomy pictures are gross? I think they're
Not
gross.
really.
They're really sometimes.
It depends on how realistic they look.
The smoker's bugs one, so I was like,
None.
None.
Okay, so I see blue cups. Are we ready to go? I can't tell where your cup is if you have a
Yeah,
cup.
it's not blue. I didn't change it.
Move it to the side so I can see it. There we go. Much better.
They
All right.
die soon. Just shoot.
So, interference, there's 2 different types. Constructive and destructive. So for destructive interference, the wavelengths must be completely out of phase. This means that they're out by a half. So this 4.5 wavelength and 4 wavelength interaction is actually, the listener's not going to hear anything. It's not that they hear something nasty there or a bad note. They hear nothing.
Is that how those
Oh, is that like when
noise?
you're screaming, like everybody's screaming and that weird tone just goes?
Yep.
Is that like how those noise canceling
Yes.
work?
Yep. So you can see this here, this R2 and R1, this is the path length. So you're comparing 4 wavelengths to 4.5 wavelengths. And it varies by an integer, so 4, plus a half, so 4.5. So the difference here would be half a wavelength.
that was a phase.
Ow.
Destructive.
No, I heard that. I'm so mean to bitch.
No, I have one
Huh? Yeah, me either.
Some places have those rooms where the room itself like it's almost, I think it's like -1 decibel, like that kind of thing.
They have more than -1 decibel.
Yeah.
The one where you can hear your blood flow.
Yeah.
That like
No,
no one
it
has
is-
lasted up to like 15 minutes in
Yeah.
that room. Like
No, I
they
think
like
it was 45. I
released
think
those.
somebody
Trial
lasted
periods that you can
45
stay in
minutes.
there. Like, would that be how, or would this be like how that kind of thing would work?
I mean, it could be part of how they do it, yeah.
So like
It's very weird shaped room too.
noise canceling headphones.
Mm-hmm.
Do they just blot out the noise or is something
They
like
create
something like
frequency
this, yeah.
opposite to what you hear.
Oh, I need my.
I smell silly voice.
what does R even stand for?
Brad.
Stands for integer.
I think it means number. But yeah, integer number, so yeah.
What's number 1 past?
That represents 1/2.
That's it, you're not getting them back.
No, I'm sorry. It's like no, it's not my fault.
Okay, we ready? We're ready. Beats. When waves are either constructive or destructive, they end up creating beats.
Vibrate.
So when two different notes are sounded together, the waves will interfere and create low and high parts. And this creates a variance in amplitude. So you can see that we have a blue wave and a black wave. And they're not really off-centered, and there are some parts where they do go right over top of each other. And there's some parts where they're perfectly canceling each other out. So we end up hearing a soft note that grows into a high note that goes not necessarily high, a louder. So this is, again, amplitude, so it's how loud it is. Loud, soft. Loud, soft. All right. So we've got this note and this note. Two different notes.
I just got excited because that red one looks like the Arctic monkey symbol.
Okay. So let's see what happens when I change that note.
Why does it keep going together? It was off and it goes together.
Mm-hmm. Just like that way.
That is so cool.
Okay, let me change the note again. It's going to go lower. It's going to get closer, getting closer to this note. It takes a really long time for it to go because there's not a lot of difference. Whereas if they're the same note, you don't hear the beat at all.
What if you get them at such a short time that the wavelengths are opposite? Would that create like noise cancellation?
If it was completely opposite, which I can't do with these, then yes, it would cancel out and you wouldn't hear anything. Because it would be constructive or destructive interference down here. Okay, so this is a much higher note. Okay. So it's like,
That's so cool.
okay, I'm going to drop it just a little bit. I'm trying to get that one where it's. So those are called beats. And this is what your band director is always trying to avoid when they're doing that. When they tune you, that's what they're listening for. They're trying to get you not to do that because it's not very pleasant.
So you know how like on a radio, like an old school radio, like where it shows like the music coming, and every time like you hear something, like you see those things fly up and then it goes back down. You know what I'm talking about?
No.
Like when the noise gets loud, it goes higher. When the noise gets low.
Yeah, when the noise gets higher,
the
it goes
amps.
higher. So is that like this or is that?
I think that's something different. Okay. So to calculate beats, you're going to take the frequency of one of them and the other, subtract. It's just a difference.
When music harmonizes, is that this?
Because you're trying to avoid that. You're trying to get them all in tune so they don't do that.
So that's like what a harmony is.
And harmony would be like C G, and what's the other one that you go in that? What's the main one? Major E, yeah. E, C, G. They all have corresponding wavelengths, so they don't go on noise. They're like wavelengths within each other. All right. Timbre, which I don't know how they got the word from the spelling, but I was corrected last year by some very high-up orchestra students. It's called timbre.
Wow.
Timbre.
Tambourine.
And that is the quality of the sound. And then, so this is supposed to be a tuning fork, by the way. A tuning fork. A tuning fork produces a pure sound in only one harmony, where a flute and a clarinet and other instruments, they don't just produce one single note like these. This would just hit it single note. If you looked at it, it'd be pure, it'd be a perfect wave. Or if you do it with an oscilloscope, it's a square wave. Square, yeah, it actually shows up square. If you do that with a flute or a clarinet, you end up with some different timbre stuff going on there. You get some quality. That's why my voice sounds different from your voice. It's because there's different things going on in our vocal cords that give us our specific thing. So when we talk, it's got some color. We call this color.
Whoa.
So you end up with these things, and this specific thing is specific to your voice.
That is cool.
So when when like you have an accent, when you fake an accent, like I can talk like bitch, like is that changing the?
I don't think so, because you're still saying it with your voice.
If you were to
You're
talk,
just
say that
saying
through my
different
mouth.
things.
So if
You're
I
singing
talk like
different
this,
notes.
if I
So
could-
these things are a little in different places, but the color of it is still specific to you.
So if I was like talking like Morgan Freeman, for example,
Then it would change a little bit, yeah.
It's really weird.
But so it's like if I could completely change my voice to sound like
Like if you can
Highlands.
imitate someone else,
I could do that.
you can change it a little bit, but it will never be perfectly their voice. It'll sound close and it'll look close, but it won't be theirs, which is why they can do voice recognition stuff. Just like lots of people can have blue eyes, but your eye is very different from someone else's eye. Yes.
Does that mean tuning fork instead of tuning?
Yes, that's what I said. Tuning fork.
I was at the eye doctor the other day, and they said that so you know how your eyes are made up of different color layers,
Mhm.
and that my first 3 layers are beige, and that's why my eyes are so sensitive to sunlight.
Interesting. Just go. You need to go. All right, we ready? Here we go. So here's the tuning fork. It's nice and pure. It only has one relative intensity on the first harmonic. That's it, just that note, nothing else. Not that pretty. I believe these pictures are in your book too, so if you need them. It's only one fundamental frequency, and fundamental frequency is the first frequency, the lowest frequency that it emits. Just so you know, we'll deal with that soon. Then this is one of a flute. You can see that it has a little bit of color here on the edges of its wave. And you can see all the different harmonics that it plays. So when you do a note, it has this much stuff going on. Yes.
Is this why pianos and, say, a flute can play the same note but sound different?
Yes, because the color is different.
So it's like each flute has its own color.
No, flutes have a color. There are, I guess, if you have different types of flutes, like a wood flute versus a metal flute, it's going to change it a little bit. But for the most part, flutes should look like this when played.
Okay.
Otherwise, it wouldn't be a flute.
Okay.
A lot of it also has to do with length. When you move your fingers, you're increasing the length of your instrument as you close down holes.
We're going to talk about that tomorrow.
Okay.
Don't get into that yet. We will talk about that. I don't want to confuse it with this. This is, no matter what note you play, it's the color of the specific instrument itself. This is like your voice. You can say lots of different things and sing at lots of different notes, or not sing at lots of different notes. it is all said with your voice. And this isn't going to change depending on what you're singing. This is you. And this one's a clarinet, so you can see a lot more color going on here. And look at all the harmonics that it has when it plays. It's very rich. We would call this a very full sound. Where flutes are kind of in, whatever. The clarinets are definitely superior.
Yes.
What about a saxophone?
Saxophone for me.
Sorry, I played clarinet for 6 years.
We get it.
My uncle plays this.
All right. So pitch. Pitch is the frequency of the note. The higher the frequency, the higher the note. So, higher than C. The lower the frequency, the lower the note. Humans can hear anything between 20 hertz and 20,000 hertz, which I think was, we saw that before somewhere.
Are we ever going to cancel out sounds in this classroom?
I don't know how to do that. I'm sorry. I don't have the equipment for that.
We can all scream really loud. Hope we all get a vehicle.
No, let's not do that. Mess with my vertigo.
We could practice singing in your class.
No singing. This is as close as we come to singing.
When you hear like a gunshot or like something explode by your ears and it goes like that's not canceling.
Are you okay?
You're too close. I don't know. I'm trying to figure out a scenario where you can cancel out noise. I want to
When
really
you're
do it.
screaming.
Are you talking about like if your ears are ringing after a really loud sound or something like that? No, that's like nerve damage.
That's like nerve.
What if you don't have like nerve, like you didn't hear a gunshot, but your ears still ring?
That just happened.
It's
You're
nerve
insane.
damage.
Okay.
All right, here we go. Here's the ear. Here's a picture.
That's gross.
And I did a lot of studying because I got vertigo last December, January, which is not cool. I'll talk about that in a second. But the sound goes into here. This is basically just like a giant satellite dish for sound, your ear. And it captures all that sound. And it puts it into this tunnel in your ear canal, which you shouldn't stick your fingers in there very far. And then this is your eardrum, which protects you from jabbing yourself in the brain. So you can't put your finger in that far. This thing can, get hurt if this fills up with fluid from your sinuses. If you go on an airplane and it gets too much pressure, it'll pop and it'll scar, and then you won't be able to absorb the same amount of sound as you would before because now you have scar tissue over it, which makes it thicker. So try not to damage your eardrums. So this, the sound goes in here, and these are the little tiny bones in your ear, and they transmit. So this moves back and forth with whatever pressure wave you're detecting. It moves back and forth, and it sends waves into the cochlea, the nasty little snail-looking thing, which is filled with gel. There's this gel in your ear, and that vibrates the gel, and then these different vibrations are picked up by the nerves in your ear, so you actually have these little tiny nerves. Different vibrations are detected by different nerves. And depending on what nerve is moved, because it will resonate with a certain sound versus nerve, it'll send it to your brain and tell you that's the sound that you're hearing. So these little things are where this gel is in here, and this is what detects your balance. Sort of, some of those things. So these things, this is what vertigo does. If everybody has crystals in their ear, but most of them are stuck up on this thing. And what happens when you have vertigo is these crystals fall. And when they fall, you turn your head and the gel moves, right? And so your eyes follow with it. Well, if you have crystals in your ears, you turn your head and stop moving, the gel hits the side, but the crystals then hit. So your eyes keep moving because the crystals have hit. So what you see is your eyes moving this way because it thinks that you're still moving, it wants to keep you upright. So what actually goes on is your eyes are moving, you're not moving, but you feel like you're moving, and your eyes are doing what they're supposed to do, but they're not. Because your eyes are connected to the nerves in your brain. So it's very hard to teach yourself not to pay attention to those things, yes.
Okay, like I know a few people who just are their eyes are constantly moving back and forth, but like in a downwards motion where they're like scanning in a ways. Would that be? They might just be
That may
weird.
be nerve damage.
That would not be this. That would be something probably not related to the ear.
Like-
What this is connected to movement. So if they're moving and then their eyes are doing it, that would be more vertigo related. Yes, Benji first.
When you, even though you're not supposed to, when you stick the swabs in your ear, and when you clean out the wax, that's the wax from your ear canal, right?
No, this stuff doesn't come out. That would be pretty much just the inside of this is skin, right? And skin gets gross, right? So that's what it is, gross skin stuff. But no, this stuff is locked by your eardrum. There are no, hole type thing. You can't get around this thing. And this stuff's locked in your ear. So once you get crystals in your ear, you can't get them out. They're stuck there. You can get vertigo 3 ways. You can get old. You can have a traumatic event like a car accident that knocks them, or have a really bad sinus infection. As far as I know, I've never had any of those, but I still have it. So, and 85% of people that get vertigo, usually it never goes away. And that's what I have. That's the thing that makes me fall over. And if you want to get rid of it, this bone right here behind your ear, it's like the biggest bone in your body. They have to drill through it, open this up, clean out all the crystals, and then sew you back up, and you'll pretty much lose your hearing in that ear. So that's why a lot of people just live with it. Okay, go ahead.
So say if you stand up really fast from like a sitting or laying down position, and then you get really dizzy and fall over sometimes.
Yes, that would be this.
Oh, cool.
Yeah.
I have no problems.
So, but that happens to a lot of people. It's not necessarily vertigo. The vertigo that I have is BPPV. It's benign proximal positional vertigo, which basically means that I have crystals floating around in here, and I'm supposed to try to get them to move up in here so that they're not in this area that's detecting balance. But I think that I've done that so many times. There's not enough room for all the crystals, so just deal with it.
I also had a serious ear infection. Like both ears.
Maybe.
So,
I don't know.
quite a problem.
This isn't just getting up and laying down. This is like everything, like moving sideways and stuff. But everybody gets a little dizzy when they first stand up. That's just maybe you got some thick gel in your ear and it just needs some time to settle. But I'm talking like full on. The whole thing looks like it's sideways, like this. I see here is this way. And when you see something like that, your brain freaks out and thinks you're hallucinating. So it sends chemicals to your stomach to vomit it because evolution says you ate berries that are making you hallucinate and are poison, so you should vomit them up. So every time I have a vertigo attack, I feel like I want to projectile vomit all over the school for like an hour.
Does anyone else get the weird thing where like you're driving and you stop at a stoplight, and as you sit there for a few seconds, the road seems to stretch out?
Yeah.
Do you actually vomit? Or?
I have a very strong stomach, so no, I do not actually vomit, but most people that get vertigo do vomit. I just don't vomit. That's not like a thing I do.
That's a no.
All right, so hearing. So a pressure wave, sound wave, reaches your ear through the eardrum. It vibrates these tiny bones that then transfer that vibration to your cochlea, which is the gel liquid. The little nerves in your ear pick up these vibrations and send electronic impulses to your brain that you interpret as sound. That's pretty much what I said on the last slide, just like written form. And I'm getting sick, and it feels like there's sticky stuff in my ear.
And you can't hear out of it. It's kind of like
I can hear out of it. It's just like before I have a vertigo attack, I feel like the inside of my ear is sticky, but it's not like the part that I can get to. It's like inside my head.
You've got something covering it?
No. It just feels like there's a hair tickling it. That's what it feels like. And what happens is if it's a really big chunk that's about ready to fall, I can actually hear it unstick as it falls, and then the vertigo comes. It's really bad. But it's down. It's like that's the only way to explain it. It's like if you had something sticky, that's what it sounds like.
So you know about it?
Yeah, I can feel it a little bit just because it tickles. But I'm sick, so I don't know if I'm going to get it or if I'm just sick. But I am starting to kind of lose the hearing on this side a little bit. It sounds like I got water in my ear. Oh my goodness, already? We're not
Good
ready.
afternoon, Pirates. Please listen up for your
Yep, there you go.
Oh, okay.
I pretty much talked about everything else, so. Yeah, I thought I had clickers. I guess I don't. Oh well.